Hello and welcome to lesson 4, where we're finally getting our introduction to limits. So we've been talking about limits quite a bit, but today we're going to put an actual definition to limits and see it in different contexts. So our learning goal for today is to define limits, one-sided limits, and the requirements for existence of limits, as well as to evaluate limits using tables and graphs. So as a warm-up, I want you to try these limits, which is just a warm-up from last class. We're just doing substitution for the values of x, for the values that they're approaching. And for all of these, you'll be able to find an actual limit. However, let's look at this first example, where you are asked to find the value of the this function when x is equal to 1. So essentially, we're trying to find limit of x approaches 1 of f of x. And why are we doing that? If you look at the denominator here, we have x minus 1. And so we see that the function is defined to not have x as 1 in its domain. So we want to find what the behavior of the function is near that point in order to approximate what the value could be when x is 1. And so I've included a diagram of this function here for you as well, where you can see that this is just a hole there because the function is not defined for that specific value of x at x is equal to 1. So we can see that their output value does not work for us through substitution. So we have to step away from direct substitution and try a different method. So just a definition here as well is direct substitution is when you just directly substitute the value of x and get an output value, which here we can see that we're not able to. So instead, we're going to approach the function at x is equal to 1 from both ends in order to approximate the behavior of the function at that point. So consider these two table of values where we're going to be approximating the output value of the function for input values that are getting closer and closer to 1 from both ends. So starting first from approaching from the left, we start at 0.5, go to 0.9, and keep getting closer to 0.1. Or sorry, getting closer to x is 1. So let's find those output values. Here we have just 1.5. Here we should have 2.7. Oh, and again for these, feel free to use a calculator just to have the most accurate answers. And finally, here we have 2.997. And now we can see that there's kind of a pattern. And our value is slowly approaching 3, which looking back to the graph, that's approximately what we needed as well. Because at this point, we see that the output value should have been 3, but the function is just not defined there. And let's also now check from the right-hand side, so starting at 1.5 and gradually getting closer to 1 by decreasing the x value. So here we have 4.5. Oh, this should be 3 and 3.003. And again, from here, you can also see that the function is approaching 3 as well for the output value. And it's just getting smaller, whereas here it's growing towards 3, and here it's shrinking or decreasing towards 3, but both ends are slowly approaching 3. So here, just a bit of notation, we write this as x is approaching 1 with that negative exponent, meaning that x is approaching 1 from the left. And x is approaching 1 with the positive means that we are approaching x from the right. So thinking of the two functions or the two table of values here. Here we have x is approaching 1 from the right because we're starting from a bigger number and decreasing to 1. And here we have x is approaching 1 from the left-hand side because we're starting with a smaller value and increasing towards 1. And so we can see that in both cases, as x is approaching 1 from the left-hand side or the right-hand side, we are reaching or approaching a value of 3. And we say that the function approaches 3 from both sides, and so the limit of x approaching 1 of the function is 3. Notice that here we are not saying that the function f of 1 is equal to 3 because remember f of x is 1 is not in the domain of this function. So this value here does not exist and we cannot say that. But we can say that the behavior of the function as x is approaching 1 is resembling that of 3. So if it was defined at that point, maybe it would be 3, but it is not defined. So we can only talk about the limit here. Now, what does it mean for a limit to exist? So here we just saw that we were calculating the limit of x approaching a specific point from both the left hand and the right hand side. So essentially what the existence of a limit tells us is that if those two values are the same, so if you're approaching a point from both the left hand and the right hand side and it is both getting to one specific value, and in this case that value is L, then we can say that the limit of x approaching that point, regardless of left hand or right hand side, is equal to that L as well. So if the limit of x approaching a from the left-hand side is equal to the limit of x approaching a from the right-hand side, which equals to L, then if and only if in this situation, then we can say that the function, or the limit of the function as x approaches a exists and it is equal to L. Otherwise, we say that this limit does not exist or DNE. Let's look now at examples where that might be the case. So consider this example, and what do you notice? So here we have the function, which is the red curve, shown to us with its graph. So you don't actually know what f of x is. So f of x is unknown, but we have the graph. And here you can see that as x approaches a, so a is this a random a value that we have chosen. Here it is approximated to be between 5 and 6 just because of this function. But again, it's any general number between 5 and 6. But we can see that at this value is where the function has a separation, where the curve is split into two parts. So as x is approaching a from the left-hand side, we see that we're actually approaching 3.8. But as we approach from the right-hand side, we're actually approaching 1.3. So the left-hand side and the right-hand side of this limit, as x is approaching a, is not actually equal. They both do exist. One is 3.8 and one is 1.3, but they are not the same. So we can say that since the function approaches two different values as x approaches a, then the limit does not exist. Or, in other words, we can say the limit of x approaching a of f of x does not exist. So we can have that the left-hand limit and the right-hand limit exist, but because they are not the same, the overall limit does not exist. Now here you're given another piecewise function and you're actually asked to sketch the graph of it. So take a moment here and try sketching this. So pay attention here. Our main point is that x is 1, where we will have the separation of the three different functions. So give that a try and I'll show you briefly in a moment what that looks like. So if you sketch the three different parts, this is what you should have got. We see that when x is less than 1, so that's why we have that hole there, because we are not actually considering when x is equal to 1. We have the function x minus 1. So labeling my graph, this part is the x minus 1. When x is equal to 1, we have that the function is equal to 1, which is just this here. X is equal to 1, or our point, or let me just, or actually I should write f of x here is just 1 because this one is also, oh, f of x is equal to x minus 1. And then finally, in this part, we have the part where f of x is equal to 2 plus square root of x minus 1. And here we can try to determine the limit as x approaches 1. So just looking at it graphically first, from the right-hand side, as we are approaching, and again, we have that hole there because it does not include when x is equal to 1, we see that we are getting closer and closer to 2. So we can write that the limit of x approaching 1 from the right-hand side of f of x, and we will just write f of x as a whole because we are accounting for all of these three because it's a piecewise function. So you have to write that f of x, which is the definition of the function. We can't just write the piece that we are using. So here, from the right-hand side, we see that this is 2. And from the left-hand side, we can see that as we are getting closer, we are reaching, so the limit of x approaching 1 from the left-hand side of f of x is actually reaching 0. And so because these two limits are not the same, so I've shown you here as well, just with the calculation, then we can say that the limit of x of the function as x approaches 1 does not exist because it does not approach a single value, so it does not exist. One key thing I wanted to go over here was this part here. So yes, I mentioned that we cannot write f of x, but here I've shown that I am using f of x, but the part of f of x as x is approaching 1 from the right-hand side is this part of the piecewise function. So if you write this, then you can split it up into the part that you are using for that x value, but you have to show me this part first. You have to show me that you're acknowledging the whole function, the whole piecewise function as one function and not as just this part. And that would be your complete solution for this problem. And we've seen now another graphical representation where the limit from the right-hand limit and the left-hand limit do exist, but they are not equal, so the overall limit does not exist. Now let's look at our root function, and it's just our parent function. So f of x is equal to square root of x. And here you're asked to determine the limit of the function as x approaches 1 by determining the one-sided limits first. So give it a try on your own. So just looking at it from the graph first, we see that we have our point x is 1 here. So x is 1. And from the right-hand side, as I'm getting closer to 1. And same with the left-hand side, I am getting closer to 1. And we can actually write this. So 1 from the right of, and here I can just write my square root of x as my function, or you can write f of x, it doesn't matter. And from the left-hand side, these two are both the same. They both equal 1. And therefore, because these two are the same and they equal 1, therefore I can say that the limit of x approaches 1 of f of x, which is the same as of square root of x, is equal to 1. Okay, and so don't forget this one with the 3 dots down is because. So you're justifying your reason. And this one we're saying therefore, or thus, or therefore. Okay, so therefore, your conclusion. Now here you're asked to find the limit as x is approaching 0 by determining the one-sided limits first. So try this as well. And let's take a look at this graphically again. So consider point 0, or when x is 0. Now from the right-hand side, we can see that as we approach this, we are getting closer to 0. But from the left-hand side, there's no function for me to approach, or no part of the curve for me to start approaching x is equal to 0. Now, why is that? Let's take a look at our function to begin with. So the square root function actually has a specific domain. And the domain, which is all the x values for which it is defined, is x is in the real numbers with the condition that x is greater than or equal to 0. So that means that our function isn't even defined for any values of x less than 0. So when determining the one-sided limits, I do have my first limit, which is x approaches 0 from the right-hand side. And this will just be um, this will just be 0. However, my limit as we approach from the left-hand side does not exist. So the one-sided limit itself does not exist, and we say because square root of x is not defined for x below 0. And this just goes back to our original definition of limits, where we need to have the secant points. And because I don't have my curve continuing past this on the left-hand side, there's no secants that I can draw so that I can find its limit and approximate the value as we're getting closer. So because of that, we just say that the one-sided limit does not exist. And then because um, the right-hand limit does not exist, then therefore the actual limit itself also does not exist, or just the any. And so here we can see that our function is defined at x of 0, and we have a very precise value of just 0 for the output, but still we can have that the limit does not exist because of the restriction on the domain. And let's look at now another example with our piecewise function where we're just going to be practicing with holes and discontinuities to see what the limit of the one-sided limits would be. So first here, look at x is 0. So this is a 1-to-1 scale. This is the scaling we have here. So at x is 0, although I have a hole, so perhaps f of 0 does not exist, is not defined, but I can still find the limit. So as we approach from the right and the left, in both cases, I am approaching, so the scale still holds there, I'm approaching 3, and this side is also 3. And so I can make a conclusion about these two, that the limit of x approaching 0 of f of x is simply 3. Now, what about for x approaching 3 from the left-hand and right-hand side? So from the left-hand side, I can see that as I'm approaching 3, and I actually do have a point there as well, we are approaching 3. But from the right-hand side, if I'm approaching 3, then I'm actually ending up at 1. And so here we say that the limit of x approaching 3 of the function does not exist because the one-sided limits are not the same. And finally, we look at when x is 5. So approaching from the left-hand side and the right-hand side, I am approaching 1 in both cases. And so here we can say that the limit of x approaching 5 of the function is 1. And notice here that f of 5 is defined for us. So f of 5 is given as 2. So we have the function defined at x is 5, and the output value is 2. This does not have to be the same as the limit. Here we can clearly see that the limit as x approaches 5 is 1, which is not the same as the output value. And this can happen. They don't have to be the same, especially with piecewise functions like this. That can totally happen, so don't let that fool you. Now, looking at our last example for today, we are given the function f of x, which is 1 over x. And we're asked to find the limit of the function as x is approaching 0. So right away, looking at the function, we can see that f of x at x is 0 is not defined. So this function itself has a special domain as well, and it is that x is all the real numbers and x is just not 0. So this is the same as x can be any value, so x can be greater than 0 and x can be less than 0. It's just not 0 itself. And here we actually have a different kind of discontinuity, which is our vertical asymptotes. So we see that the function is just reaching the y-axis and it never actually touches the y-axis. It just gets infinitely um, or as we continue to infinity, it keeps getting closer and closer. And same with this side, we're getting closer and closer to the y-axis, but we never fully reach it. And horizontally, we see that in these two cases, they are also reaching the x-axis, getting closer and closer, but never directly reaching it. And this one is our horizontal asymptote. So going back to looking at x approaching 0, so from the left-hand side, I'm following the function this way. And I see that I'm actually getting um, my value is getting closer and closer to negative infinity. So I'm getting, my value is getting larger and larger and larger, but um, in the negatives. So eventually it's going to become really large as we keep going, and we'll never reach an exact value. And so that's why we represented with infinity. And now I want you to try to think what this one would be as x is approaching 0 from the right-hand side. In this case, if I follow my function and keep going towards x from the right-hand side, I see that the output values are getting bigger and bigger in the positive side. So here we also have that we're approaching infinity, but now positive infinity. And in this case, we do have two infinities, but negative infinity and positive infinity are different. In this case, you're going down, and in this case, you're going up. And you can clearly see that on the graph itself, that at x is 0, the function is going in different ways. So that we say that the limit of the function as x is approaching 0 does not exist. And so that's our conclusion there as well. We can conclude that because the one-sided limits are different, then the overall limit does not exist. And so this was to familiarize you with limits that reach negative and positive infinity. Those can happen. Here we can also, another representation you might see is me asking you, what is the limit of f of x as x actually approaches infinity? I could ask you that too. And here we're actually looking now at the function behavior as x is getting infinitely larger. And you can see that just by looking at the graph, this is approaching um, uh, is approaching 0 because we're getting closer and closer to that 0 line. And here we do have it defined as that because we don't really look at the left hand and right hand limits. Because with infinity, you can't really look at it that way. But regardless of any point or any interval you look at down the line of this graph, you'll see that this holds true. And same with the opposite side, if we do x is approaching negative infinity, so looking at the function as we're going towards the negative infinity for x, we can see that this one is also approaching 0. And we'll actually have that positive and negative here as well in our powers. So here we're going to have this, and here we're going to have this. So the reason for this is from the, as x is approaching infinity, you're reaching or you're approaching 0 from the top. And in this case, you're approaching 0 from the bottom. So this is the approach from the top, and this is approach from the bottom. And that was just a little mini side lesson as well with infinity in limits, but we'll go over that in more detail later on. So for today, just completes the practice lessons. You do also have a discussion question, so please take some time to read that, and respond to a classmate. And as always, if you have any questions, please don't hesitate to reach out, and I'll see you all next class.